This video will cover fighter and bomber weapons with advice regarding aircraft design. Later videos will cover topics of basic maneuvers, 1v1 maneuvers, section tactics, division tactics, unlimited aircraft, fighter missions, and tactical intercepts. First, fixed forward guns. Fixed forward guns are guns which are pointed forward of the plane's flight and cannot be rotated in any significant way. Fixed forward guns have several major advantages. Their installation is lighter and easier, FFGs have less drag force, less negative impact on performance, and maneuvering is simpler. For all these reasons, fixed forward guns are preferred for smaller and offensive aircraft, meaning fighters. The advantages to flexible guns are, firstly, they can be aimed independent of the plane's direction. 2, they can fire in multiple directions at once if there are multiple guns. 3, aiming can change faster. For all these reasons, flexible or moving guns are preferred for larger and less maneuverable aircraft because they cannot maneuver to have their enemy in front of them. The prime example of this is the B-17 Flying Fortress, a heavy bomber which had twin 12.7mm turrets under the nose, aft of the cockpit, under the fuselage, and in the tail. This worked better because the bomber had to fly straight towards its bombing target, making it too time-consuming to maneuver to put enemy planes in front of it. Now for some terminology. A cannon is a gun that fires explosive bullets. The explosive charges are armed by acceleration and then implode on impact, generally sized as 20 to 40mm bullets. Cannons have increased damage per hit, however they also have a lower fire rate than regular bullets, and the gun is larger and heavier than regular guns. However, on that note, it should be mentioned that some wing designs can be so thin that explosive bullets pass right through without exploding. This happened when the more advanced guns of the Kriegsmarine's Bismarck fired on World War I era British fighters with canvas wings. Now, several trends in aircraft design during World War II. As the war progressed, the firepower of fighters increased, there was increased target specialization, standard US fighter armament became 6 or 8 50 caliber machine guns mounted on the wings, and the Germans increasingly used cannons, especially for fighting heavy bombers. Throughout both World War I and World War II, guns were placed varyingly at both near the fuselage and on the wings. Now we will discuss the advantages and disadvantages of wing-mounted guns and their different configurations. Centered guns will not be talked about for now. Designs with wing-mounted guns' main problem is bullet dispersion becoming excessive. This problem has been attempted to be solved by various methods. The first method is point harmonization, where guns are angled to hit at a point far off in front of the plane. The disadvantage of this method is that it requires good marksmanship. The second method is pattern harmonization, where individual guns are slightly adjusted left, up, down, or right. This design is better for more damaging guns where hit concentration is less important. The disadvantage is that the designs are more complicated structurally, and it distracts the pilot from their plane's overall movements. Actual damage estimates per bullet are complicated, and a subject I will go over in a separate video. Aircraft design with uneven weapon distribution will require rudder adjustments to match. Here I will also mention that guns can cause two different types of errors with plane performance. 1, the gas from bullets being fired can interfere with engine performance, so some distance must be placed between the components. 2, the knockback force from firing a bullet can slow down planes, especially slower flying ones, and risk stalling the plane. Quick note, tracer bullets, bullets which are so hot that they glow and are extremely noticeable, are terrible for being in planes. They belong in anti-air guns placed on the ground. Air-to-air gun sights. The earliest sights were a ring and bead design. The bead would be aligned with the front of the plane, then fire. Maximum effective range was when the wingspan of the enemy aircraft extended over half of the diameter of his sight ring. If you see the enemy plane or bogey here, then you will want to pitch up by pulling the joystick back. If you see the bogey here, then you would turn to the right, pulling the joystick right. One big problem with this design is that any movement of the pilot's head will throw off the estimates. Gyroscopic Computing Lead Optical Sight, GLOS. The three components of a GLOS are a sight display unit, a gyroscopic sensing unit, and a computer. The pilot will hold the pipper on the target, and then the computer will calculate target range, speed, and then the required lead angle. The computer will take a minimum amount of time to calculate, and any rapid changes in pipper location will throw off the computation, making it take longer. Radar can provide automatic ranging. Guns have both a minimum and maximum range. Max range is based on accuracy and effectiveness of bullets. The minimum range is based on preventing your plane from being in the debris explosion range of the destroyed target. Advice regarding how to maneuver against the target is this: the opponent must be beaten first, then shot. Guided missiles. This section refers to missiles that change their flight paths in response to maneuvers. Unguided rockets may be thought of as big bullets and use the same tactics as guns. The different types of guided missiles are air-to-air, surface-to-surface, surface-to-air missiles, and air-to-surface missiles. This section will deal primarily with air-to-air missiles. From an engineering standpoint, the range of missiles can be increased by increasing the size of the rockets. From an engineering standpoint, the range of missiles can be increased by increasing the size of the rockets. However, greater weight will also grow complexity, weight, and drag force. So the design of the missile should be carefully optimized, and its launch and guidance systems should be taken into account when designing its aspects with the plane. Now on to the different types of guidance. The first type of guidance is preset guidance, where pre-launch determinations are based off missile target interceptions in space before launch. The guidance system is provided with trajectory for missile destination, and this cannot be changed after launch. This is closely related to an unguided rocket. 2. Command guidance. This is similar to classic remote control positioning of target and missile. Monitored commands are sent to the missile to guide its flight to the target interception, which is usually done by radar, but can also be done by electro-optics on site. Radar is best, though. Guidance instructions are susceptible to jamming. Beam rider guidance is where the missile is designed to seek and follow the center of a guidance beam. Beam rider guidance can also come from target tracking radar, electro-optics, or a visual system. Beam rider systems are not limited to daylight and good weather, but they are more susceptible to electronic countermeasures. One problem with beam rider systems, as with command loss, is missiles must have high maneuverability to intercept evasive targets. This problem can be mediated by using two radars, one for the target and one for the missile. However, this is rarely done. The third type of guidance, and the most effective type, is homing. The subtypes of homing are passive, semi-active, and active. Passive homing relies on emissions from the target. These emissions could be sound, radio waves, radar heat, or light. Semi-active homing guides on energy reflecting off the target. This is provided by a source external to the missile. Active homing. In active homing, the missile itself illuminates and tracks the target. Active homing's main drawback is it requires more expensive and complicated missiles. Figure 1-7 illustrates missile trajectories. Pure pursuit always turns to point towards the target, lead pursuit aims just ahead of the current target, and LC is more predictive, way ahead of time. And start with pure pursuit. Here, if we follow the lines from the start point to the target track, we can see that at each point in time, the missile is aiming at where the target currently is and plans to intercept at time 5. If we follow the lead pursuit path, we can see that at time 2, the missile is aiming just ahead of the target at time 2, and the same follows at 3, where now it is almost pointing to time 4, and at time 4 is pointing to LP, where it plans to intercept with the plane and explode. The lead collision course calculates that the plane and missile can intercept at time 4 at point 4, and so immediately heads for that direction where it plans to intercept the plane. Passive homing systems usually follow a pure pursuit. This is because pure pursuit is easiest to program for guidance computers. Beamrider and command-to-LOS systems use lead pursuit commonly. To compute a lead collision course, a process known as proportional navigation is used. This involves turning the missile until the heading is found which stops the target's apparent lost drift rate. Proportional navigation assumes the target is traveling in a straight line at any moment. Should the target be maneuvering, constant angle changes are required, which is not advantageous. Collision guidance systems most commonly use proportional navigation principles. Missile seekers have a preset command guidance system that does not require a seeker beam. Rider missiles usually have a receiver in the tail and a sensor receiver in the nose, as do semi-active homers. Semi-active homers also include a rear receiver for interception of information. Active homers require both a transmitter and a receiver, which is generally located forward in the missile. Passive seekers have an inherent advantage because passive range varies inversely proportional to the square of the target range, while the max range of active and semi-active systems varies inversely with the fourth power. The most common passive seeker type is now the heat seeker missile. Missile warheads are typically blast fragmentation types, incendiary, explosive pellets, or expanding rod types. Blast fragmentation warheads are intended to cause damage through explosive shock and high-velocity fragments. Pellet designs are similar, except fragments are small bomblets that explode or burn on contact. Fragments rapidly lose killing power with miss distance being the distance the missile exploded away from the edges of the plane. This can be solved by greater explosive power or incendiary pellets because one hit does more damage. Expanding rod warheads are comprised of short lengths of steel rods placed side by side around explosive material. They are all welded together at ultimate ends so they expand outward in a solid continuous ring that can cut through hydraulic cables and fuel lines and other structural members. However, this actually leaves large gaps in warhead coverage. You can picture this design packed into a shell that then expands outwards in a circle and cuts a circle slice through the enemy plane. Warheads should be designed with specific targets in mind. The boundary is the range at which the missile is capable of guiding to within lethal distance of the target. The secret limit line shows the tracking limit of the radar seeker. The lookup required zones are associated with ground clutter. Hot side and cold side refer to inside and outside the enemy's plane's turn direction, respectively. The psychological factor of a missile coming at you should also be taken into account in dogfighting. If you are finding it hard to keep track of all these details or become worried about the gaps in knowledge from the missiles, plane sight, and other problems, then you are close to understanding the importance of knowledge and communications integration in weapons and recon systems. The upcoming fighter that does this excellently is the F-35. The F-35 has great systems that coordinate weapon systems between multiple fighters. Engineers can also take into account defensive capacities that may protect their plane. Defensive techniques can be divided into noise and deception. Noise jamming produces a strong signal that will overpower the target. Return. Doppler radars are less susceptible to jamming. The effectiveness of noise jamming is related to the ratio of jamming power received to strength of target return. Noise is more effective when concentrated in a beam at the enemy radar. The most common form of infrared countermeasure is the decoy flare. Defensive ECB and defensive ECM must be highly automated. The elevation or air density should also be taken into account with which missile type will be most effective. If this is an interesting subject, I will go into this in a more detailed video. Please comment below if you want to see that. So that's all I have for fighter weapons in this video. Later, I will cover the rest of the topics mentioned at the start of the video. Thanks for watching.